All right, good morning. It is actually like a couple of hours before our class starts. It is like it's what like 10:45. So, yeah. All right. Anyway, right? We solved that problem earlier about the Grashof criterion, and now we will continue a little bit more into Grashof's law, although this is no longer quite Grashof's law. Although it's still related because it is going to be way different from what we want to discuss today. Although we're still gonna have a couple of problems anyway, right? When we have four bar linkages or any linkage for that matter, we usually use them to transmit either motion or power. And in those two instances, right, you want to take care of, or rather, be aware of any optimal configuration, right? And in this case, say for example, we now have this new problem right here, this new kind of problem 3.3, wherein you're going to have to find the minimum and maximum value of theta in this following linkage. We have here a 4-bar linkage, no big deal, right? This is the crank, right? This left side, this turning link will be the crank. This is the coupler, and this is the other link. And we have these measurements right here. We have 4, and then 8, and then 7, and then 10 for the ground. And basically, this is what we want to find, right? A minimum and a maximum value for this theta right here. And so you might say to yourself, okay, what does this have to do with our previous slide? Well, if you're going to transmit motion, you at the very least need to know, right, what this linkage is, number one, right? And then after that, if you can find out what type of linkage this is, what kind of motion you're going to impart. If this is going to be our crank, or rather the thing that we're going to actuate, because at this point we still don't even know, right, what type of linkage this is, right? We should at the very least be able to predict the output, right? The output should be between, right, something like this or like this, right? For all we know, this could be a drag link, and well, there is no maximum and minimum value because, right, it will go a full rotation, right? But let's just see, find out, right? We have SL and then PQ here. We have our shortest link, which is the 4, and then the longest link, which is the 10, and then the two other links are the 8 and the 7. We will have 14 and then 15. This seems to be correct in the sense that hindi naman correct, sorry, less correct, more in the sense of this follows the Grashof criterion, which means at the very least one of them, right, one of the links in here is able to rotate, right? And if we remember, right, that one of them is a crank, if the shortest link is the turning link, then at the very least we know that this is a crank and that this is a rocker, right? So this is now a crank rocker linkage. That means at the very least we are able to think that this is going to only rock from a certain point up to another point. So that is the kind of thing that we want to get from this problem, right? It's going to rock from left to right, and we need to find the leftmost and the rightmost configuration. And how we're going to do this is, well, you can cycle through in your mind, right, how it's supposed to be. Let's not go here, and let's instead go somewhere here, right? We're going to have in here the same configuration, right? 4, 10, 8, and then 7, right? And what we're going to see in here indeed it is a crank rocker linkage. If we're going to let it run for a few moments, you'll see that the path traced by this rocker is this to here, right? From left to right. There's a leftmost configuration and there's a rightmost configuration. This is a bit of a cheat in the sense that we can actually visualize it, but I think this is the best way for you to be able to find out where the minimum theta is and where the maximum theta is, because, well, no one cares, right? Like if you're going to get this through like straight up geometry, good job, right? If you're just gonna visualize it, well, we have the tools to get the visualization, and I have to tell you that the minimum path, or rather the minimum theta, is achieved when a special property is achieved, right? In this case, look at the coupler and the turning link in here. It seems like they're almost overlapping. And in this case, what you create in here, what we're able to create, is this small triangle. On the other hand, the maximum theta you will get from this, right? And it seems like at this point, there's another property, very interesting property, wherein the turning link and then the coupler, it seems like they're making just a straight line, right? Imagine if we make this line straight, right? We will then be able to get the maximum theta in here. And that is the clue, or rather that is what we need to do, right? This, for us to get the minimum theta, they need to completely overlap, and for us to get the maximum theta, they need to completely add up, right? And so that's what we're going to do in here. We will have this, right? We will have this. Actually, I want to have it on the grid. So this and this, I know that those are 10 units, right? So that is 10. Right? That is 10. And then on our first layer, we will have, right, our minimum theta here, which is something like this, right? As you can see in here, the 4 and then the 8, they're going to subtract from one another, right? There's a 4 in here, and then there's going to be an 8 in here. Right, there's going to be an 8 in here. And so that means if this red link is 4 and this is 8, right, what counts in the triangle is just going to be a 4, right? That is the 4 that we see in here. Okay, and this other link right here is a 7. So that means, well, we now have a triangle that is 4, 7, and 10. And therefore, what we need to find in here is this theta, which means, right, we are dealing with an oblique triangle, right? Why do I know that we are dealing with an oblique triangle? Because number one, I seem to have done it somewhat properly naman, right? I don't know, it kind of looks the same, right? As similar to here, and it's very clear that this is not a right angle, right? And if we want to check, right, let's just try and put these things in a Pythagorean theorem configuration. Is 4 squared plus 7 squared the same as 10 squared? Let's see, this is going to be 16 plus 49 is going to be 100. Clearly not. So this is not a right triangle. However, there is a generalization to the Pythagorean theorem, and that, of course, is the cosine law. The cosine law states that, say, for example, if you have any oblique triangle, let's just draw an oblique triangle. Is this right? No, this is right. Okay, let's try and draw. Okay, it doesn't recognize. Sige, let's just draw 3 lines. Yeah, there you go. If we have a triangle right here, and we know that it is not right, it is not anything like that, right? And we have values of A, B, and C, what will happen is that their corresponding opposite angles will be called the big letter, right? The big letter version of their side lengths. So this one is going to be angle A, this one is going to be angle C, and then this one is going to be angle B, right? And so the cosine law states, right? We need to make this in yellow, right? The cosine law states that the cosine law states that if you want to get, right, a relationship between the 3 lengths and a particular angle, say for example angle A, what you're going to have to do is something like this. You want to get, or rather you want to get the relationship for A. What you're going to do is take the side length of A, right? So A squared is equal to B squared plus C squared. And then you might say to yourself, wait a second, this just sounds like the Pythagorean theorem. Yes, this is where it comes from. And then you're going to add in here a kind of an adjusting term, right? Adjusting term minus 2BC, whatever is on the other side. You multiply them and then you cosine A. Why this works as the Pythagorean theorem is that if you think about it, the thing, or rather the angle opposite the hypotenuse would be 90 degrees. That is by definition a right triangle. And if you get cosine of 90 degrees, you just cancel this out. And that does become the Pythagorean theorem, right? So if you guys didn't catch that, right? If this is our right triangle, right? The thing across, right? The opposite angle of the hypotenuse is always going to be the right angle, right? And then of course cosine of 90 degrees is 0. Okay? And now, how are we going to use this? Well, we want to get the theta in here, so let's just try and pattern this the same way we would, right? In here we will get, right? In here we will get 4 squared, because that is the thing that is opposite the theta. 4 squared is equal to 10 squared plus 7 squared minus 2 times 10 times 7 times your cosine of theta. And so honestly, you don't need to like be very meticulous with this thing. You can just isolate cosine theta, and here you will get 4 squared minus 10 squared minus 7 squared, right? You're just moving everything to the left, and then you're dividing by negative 2 times 10 times 7. And so, as a result, what you're going to get is this, right? And you get a theta minimum of what? Our cosine, this value, right? 4 squared minus 10 squared minus 7 squared all over 2 times 10 times 7, that is just negative 140. Okay, so let's try this out. And of course, be sure that you are on the correct side of your angle units. Baka naman mamaya, you don't remember that you are in your radians, right? So that's gonna get you a really different answer. Negative 140. We will get an answer of 18.19. So that is our minimum theta in here. That is our first answer. That is for our minimum. And now for our maximum, what we're going to do instead is we're going to add up the blue and the red links, right? The red link is the turning link, which is 4, and then the blue link, which is going to be 8, right? So we will have in here 4, maybe something like this, 4, and then the blue link, which is going to be like this as well, that's going to be 8, and I don't think that's the right, it's the right configuration. Maybe something like this. Oops. Something like this. 4 and then 8. Maybe. Like this. And then this is your 7. Does this sound right? Or does this look right? I think. Yeah, maybe it does. Yeah. So this is your 4. And this is now your 8. Right? And basically now we want this as well. This. And so we can see that this is just going to form 12, 7, and then 10, right? Oops, 10. And same, just like before, right? And if you want, you can just write this down again here, right? 12 squared is equal to 10 squared plus 7 squared. Oops, 10 squared plus 7 squared minus 2 times 10 times 7, and then cosine theta. So honestly, the only thing that changes now for your theta maximum is this thing, is this value, r cosine of, right, 12 squared minus 10 squared minus 7 squared all over negative 140, which will give us a value of 87.95. So very close to 90 degrees. 87.95. Okay, so that is how we get the minimum and the maximum values. So apparently in this case, we are looking at somewhere like 18 degrees. And in here, we are looking, it does seem like a right angle. Now that I look at it, right? Almost like a right angle, 87 degrees. Okay. Okay, so that's how we get the minimum and maximum values. On the other hand, right, if you want to transmit power, you will have to look at the transmission angle. Literally, the angle wherein you transmit a force. Or more specifically, in this case, because you're thinking of motion, or rather of rotary motion, forces are less important, more so torques. Right? If you remember torques from before, from like literally any other physics course that we have, right? A torque is what happens when you impart, right, a force along a certain moment arm, and that causes rotation, right? Because you are not imparting it on the line of action of this axis, or rather on the axis of this axis of rotation. It does not cause translation, instead it causes rotation, right? And what we need is that this needs to be somewhat perpendicular to the moment arm. Because if it's not, say for example, something like this, right? You will find that only the horizontal or the perpendicular component gets counted as part of the torque, right? And of course, we want to impart full power, full torque, and so as much as possible, we want this to be, right, at a 90-degree angle, right? So that is for ideal power transmission. But in this case, right, the transmission angle in linkages like this, if you know the input link, right, will be the angle between the coupler and the driven link. It's not the driving link or the input link, it's the output link. It's whatever you want to push. It's whatever you want to transmit power to. Right? So in this case now, instead of finding theta, right? Instead of finding theta, that is the input link, that is the output link, it will still have the same bits. This is your transmission angle, right? And now we want to find the minimum and maximum value of gamma gamma in the following linkage, right? And so now you might think, right, how are we going to get maximum and minimum values of this thing, right? So go ahead if you want, right? Try and figure this stuff out. I will give you the visualization here. Excuse me. And just feel free to pause, or rather just like look at this thing, right? See where the maximum and minimum values of your gamma are. Because I can see them in here, I suppose, right? Okay. Sige, let's let that run through a little bit more. And then I suppose we can stop, right? And now, if you've seen, right, this is where you will have your maximum transmission angle, right? This is very wide. And in this case, if you're thinking of this, right, this output link being the moment arm, of course you would want, actually, you know what, let's take a screenshot of this. Oh, that's what I should have done in the beginning. Okay, let's take a screenshot of this. And what we're seeing in here is that, say for example, this thing, this coupler is of course the one imparting the force onto our driven link. However, the driven link has a moment arm that is like this. And so if you want to transmit torque, the only thing that gets counted, the only force that gets counted is this. Oops, this, right? That is the only thing that gets counted, right? Yeah, there you go. That is your right angle. And so it's not transmitting everything that you want it to, right? That is why we want the transmission angle to be just at about 90 degrees. So this is your maximum transmission angle. And then this is your minimum transmission angle. This is the smallest it can be, right? And what do you notice between these two configurations, right? Instead of this thing lining up the input link and the coupler, what is happening now is that the input link needs to be lining up with the ground, right? We want the longest and the shortest triangle possible in terms of the transmission angle, right? And so what is happening in here is that you will get the maximum if you see that these two are connected, right? This is your 4, this is your 10, and basically we are creating in here a triangle that is 4 and 10, that is 14, and then 8, and then 7. And still, this can be taken care of by the cosine law, right? This can be taken care of by the cosine law, but now your gamma is here, so we're gonna have to 14 squared is equal to 8 squared plus 7 squared minus 2 times 8 times 7 times cosine gamma, right? And in this case, your gamma will be arc cosine of, right? Arc cosine of 14 squared minus 8 squared minus 7 squared all over negative 2 times 8 times 7, that is 56 times 2, that is 112. There you go. So let's try this out. 14 squared minus 8 squared minus 7 squared. And then negative 2 times 8 times 7, we will have a maximum of 137.82. 137.82. So this is our maximum, right? This is our maximum gamma. Right? And our minimum gamma comes from this, right? This configuration. I'll just take a picture of this. There it is. And then we'll have it here. Let's line it up. Okay. And then we will have basically, if this is 10, right? If this is 10 and this is 4, what is happening is that 4 and then 10, this creates a 6, right? A 6. And then it creates basically just another triangle here. 8 and then 7. Okay? And we will have here our minimum gamma, which is just again, right, applying the cosine rule. Honestly, we can do this immediately, right? Our cosine, right? Since you guys already hopefully can see the what do you call this? The pattern, right? 6 squared minus 7 squared minus 8 squared all over negative 2 times 7 times 8. You will have 46.57. 46.57 degrees. So there you go. Honestly, it does look like 45 degrees if you like tilt your head a little bit. And then this one here should be, I mean, like, I don't know how big that is, right? That is 137, which is kind of like 135 degrees Celsius. Oh, Celsius tuloy. It's like this, right? A 90-degree angle and then a 45-degree angle. So it is kind of like that, right? 137.82. Okay? So, yeah, when you are transmitting power, right, you should look at the transmission angle, right? However, if you're trying to transmit motion, in this case, what you should look at is the left and rightmost components of your output link. Not components, but the positions and the orientations of your output link, right? That is what we're supposed to see. And honestly, this can also apply for crank slider linkages, right? Crank slider linkages, if you guys remember, right? This one here. And then this one, say for example, something like this, right? And then say for example, they are lined up. And there you go. Yeah. The transmission angle of this thing is here, right? And instead of thinking about the left and rightmost swings of this rocker, what you're supposed to indeed find is the left and rightmost configurations of this slider, right? But yeah, we're not gonna have this because we mainly focus on 4-bar linkages, but hopefully you can point out in future references, right, where the transmission angle is of this thing, right? In essence, right, when you want to transmit motion, of course, you're turning rotary motion into translational motion, right? You should be able to pinpoint where the extreme positions are, right? The leftmost and the rightmost. And if you're transmitting power, of course, again, we're going to have that thing wherein this is your moment arm. And what you need to do is you need to get this as close to 90 degrees as possible to transmit the most amount of power, of torque, which means the most amount of power, right? So now that that's done, how long have we been recording? We've been recording for 24 minutes. So I feel like I'm going to have to extend a little bit, right? We just need to get this out of the way, right? Robotic manipulation. Of course, when we're talking about, right, machine elements or basically stuff like that, it is not impossible for us to think about, robotic arms, stuff like that. Especially given that, we have seen kinematic chains, something like this, a ground link, and then you have this crank that can rotate all the way. You have another crank here, open, that rotates all the way, and then you have an arm, a robot arm, that can also rotate all the way. The thing about this is that this is technically an open kinematic chain. Say, for example, we have here ground link 1, this link 2, this link 3, and this link 4. Right? And you have a revolute joint, another revolute joint, another revolute joint, right? And just to get the mobility of this thing, right, you will get, right, this NL minus NJ minus 1 plus all of your connectivities, right? And you will get 3 times number of links 4 minus NJ is 3 minus 1 plus all of the revolute joints are just 1 each. So 1 times 3 is 3. And you will see 4 minus 3 minus 1 is just 0. So all of this gets cancelled. The mobility of this is 3. That means that this robot arm is fully articulated when you install motors on all 3 of the joints. That is what happens, right? And so basically, this rotation right here is independent from, yes, that rotation right there is independent from this rotation right here, which is that, right? And it's also independent from this rotation of the arm like this, right? So all 3 of those things are independent of one another. All 3 of those thetas are independent of one another. And so now, this sounds like, I don't know, some problem you encounter at a warehouse, right? Of course, when you're moving stuff around, right, you need to be able to put the robot arm where it's supposed to be. Let's say, for example, on top of a shelf, on the ground, right, on a forklift, something like that, right? And basically, we encounter some interesting problems. More specifically, 2 problems, right? And it seems like they are just the same, but they're a bit different in the sense that, well, now you're going to ask, if you want a particular position, what parameters, or rather what joint angles do you need in tandem to grant that particular position, that particular orientation? On the other hand, the flip side is, right, if you get a bunch of joint angles together, what position will you get, right? What orientation will you get? So they are the opposites of one another. Kumbaga, the first one is you're trying to reverse engineer based on a position that you want. How will you get that position, right? What angles will you need to find? And on the other hand, right, when you have input parameters, input joint angles, what kind of position will you get? And so in here, we will get what we call forward kinematics, basically forward, right? If you have joint angles, link lengths, if you have those input parameters, right? Your input will be your theta 1, your theta 2, your theta 3. We didn't even discuss that earlier, but you can also have link length 1, link length 2, link length 3, or whatever, right? Your output will be a particular position of the what do you call this? Of the robot arm, right? This is your output. On the other hand, right, if you have this notation, the inverse should also be true. Literally, inverse kinematics is now the other way around. You are now going to try and reverse engineer the possible solutions, and you don't even know if there is a solution, wherein if you have, right, an input position, say for example, something like you want the arm to pick up something in here, what kind of output, what kind of joint angle combination and link length combination is possible, right? Is it even possible? We don't know, right? Maybe there is a what do you call this? There is a solution like this. Maybe there's a solution like this. Maybe there is no solution. We don't know, right? Usually the number of solutions is there's no solution, there is 2 solutions, there's 1 solution, right? But in this case, we will dive more deeply into forward kinematics, right? Just to let you know that there are 2 kumbaga approaches to solve this kind of problem, right? And for those of you who are interested in robotics, I feel like you have seen this before, although now we will put some more math into it, right? when we have this configuration, we will have what we call an end effector. Literally, this is the interesting part of the robot. This is the thing that interacts with the environment. This is the thing that grips objects. This is the thing that, I don't know, you use to sense something like that, right? End effector, right? This is the point of interest of our robotic manipulator, right? On the other hand, we have, right, this thing, right? We have this thing. So you might say to yourself, wait lang, is this degrees of freedom? No, this is just a reference frame, a fixed frame, literally a set of coordinates that is anchored to the ground, right? That is anchored to the ground. The thing about this fixed frame is that this is made as the reference for everything else. We are seeing this robot in 2D. That means we have two coordinates, an x coordinate, or rather an x-axis and a y-axis, and basically every other link will have its own frame because it is oriented in a certain way. If we remember from earlier, right, the default position of this robot was just lying flat on the ground, literally something like this. Okay, and so we will see that there is a particular frame for each of them, right? And so if you're going to orient yourself like this, you will see that they are flat, right? If you turn your heads to wherever the frames are, right, you will see that they are supposed to be like this, right? Like this, and then like this, right? Those are what we call your reference frames or moving frames for each of the links. Each link here has a moving frame, and this is just so we can orient ourselves if ever this robot moves, right? Or sorry, yeah, if ever one of the links move, we will be able to tell because the frame has now changed, right? And so we have other things, of course. We have position, right? Literally just the position. And now here's where you're going to have to encounter matrices, right? Vectors, right? Position in this case is denoted by the letter P, right? And it is a vector containing the coordinates of a link. Literally, say for example, you have P, which is, I don't know, 3, 4, right? This now corresponds to the X coordinate and the Y coordinate. So just like a vector, something like this, right? 1, 2, 3, 1, 2, 3, 4. Your your position is something like this. So maybe it corresponds to a link that is like this, right? And maybe another link is like this, so it looks like this, so on, so forth, right? And right, how are we able to move these things? They can move based on what we call transformations. Transformations literally just take you from one location of an object to another location or another orientation, right? And in this case, there are 3 kinds of transformations. One that is just pure translation, which is something like this, right? Makes sense, right? Say for example, maybe a link is right here and it brings it much farther, right? Or just to another different location. Notice that the link in here did not rotate, right? Literally, it's just pure translation, okay? So say for example, we have here a cylinder, right? Or a prismatic joint. That prismatic joint just extends, okay? So in this case, we can model pure translation as just something like this. If we have your initial position, and if we have this displacement, letter D, what we can literally do is transfer that over there, and we can now see that there is, kumbaga, a ramp for this position vector to move to there, right? So that is how we model pure translation. You literally just add this vector, this P0 vector, to this displacement vector, right? Very simple for now, right? And of course, I am under the assumption that you guys have some preliminary knowledge about matrices, right? So this is available, or rather, this is a possible kind of operation because they have the same size, right? They have the same size. Both of these matrices are 2 by 1s, right? 2 rows and then 1 column. That means that you can just add them, and that means that your P1 in here will just be equal to x0 plus delta x, and then y0 plus delta y. That's it, right? Next, we will have pure rotation, which is literally just this, right? And so how do we model this thing? This is where it gets a bit annoying. This is where it gets a bit what do you call this? This is where it gets a little bit unmanageable, right? In this case now, we can no longer just add matrices together if we want to go from here to somewhere here, right? In this case, we now have to do what is called matrix multiplication. This is what we call a rotation matrix. A rotation matrix. And basically, that rotation matrix depends on the angle that you want to rotate it by. Right? Oops. And the rotation matrix basically looks like this. This is for a 2D, right, rotation. Right? This is for a 2D rotation. Right? You will have cosine, and then sine, and then negative sine, and then cosine. So sometimes for ease of writing this down, we can just write the cosines as letter C, and then you can write the sines as letter S, right? Hopefully this is still understandable to you guys, right? Sometimes they even do it like this: C sub theta, negative S sub theta, and then S sub theta, and then C sub theta. This is also acceptable, right? I can accept any of these things. And the thing about this is that they are dependent on this angle right here. And notice, this is always counterclockwise positive. We are no longer operating under the operations, under the protocols of, say, for example, NMEC 1, NMEC 2, right? Or NMEC 3, basta any of the NMEC series, right? It's not enough that we just say, you know what, I will treat this as blank. Because the cosine and sine have a convention, have a certain convention to them, your angle will always start counterclockwise, right? Just like how we say this is 0 and we go to 90 degrees. That is a counterclockwise rotation. Okay? So if we want, we can try this out, right? First with, say for example, a graph like this, right? Very simple graph. Very simple graph. Let's have a little graph right here. Right? Say for example, I have here a vector, and as you can see, the grid lines tell me that this vector, this position vector, is initially, this is 2 and this is 1. So this is 2, 1. Okay? Say for example, I want to now rotate it by 90 degrees. Right? 90 degrees, if you look at this, this will now become, right, your P1, which has coordinates of, this is now negative 1 and then 2. Negative 1 and then 2. Let's just see, let's just confirm if this is indeed correct, right? The rotation matrix is correct. And how you're going to do this is P1 is just equal to your rotation matrix for 90 degrees, right? Times your P0. And I have to say, it will not work if you do it like this, right? Matrix multiplication follows a certain order, and you will know that order because, right, you know the sizes of your rotation of your matrices, right? Your rotation matrix, your general rotation matrix looks like this, right? Cosine theta, negative sine theta, and then sine theta, cosine theta. This is a 2 by 2 matrix, literally 2 rows, 2 columns, right? And this thing is a 2 by 1 matrix, 2 rows, 1 column. And it will only work if, look at this, 2 by 2 and then 2 by 1. It will only work, matrix multiplication will only work if these two touching numbers are the same. Right? And you can also predict what the size of this thing is. If you just remove those two, you will see a 2 by 1. You will get in here, right, by multiplication, a 2 by 1 matrix. So again, right, hopefully that's not like a big stretch. Right? Say for example, 3 by 2 matrix times 2 by 1 matrix. You will get a 3 by 1 matrix. But in this case, this makes sense, right? Because this is also a position vector, right? So what we will do now is we will just try and compute to see if this is indeed correct. Cosine of 90, we just said earlier, is 0, right? And then sine of 90 is 1. So this is negative 1, this is 1, then this is 0. And we will look at 2 times 2 and then 1 pala, sorry. And, right, if you remember matrix multiplication, it will go row times column. right? Row times column. Let's see if this is indeed correct. Row times column, right? What you will do is look and count, right? From left to right and up to down. Left to right, up to down, right? What you will do now is this times this, 0 times 2 is, well, 0. And then negative 1 plus 1 is, negative 1 times 1 is negative 1. This is negative 1. And now we can see, okay, right? And then we will now count this, row times column. There's only one column in here. There are two rows in here. So there are two possible combinations. We will now have here 1 times 2 is 2. 0 times 1 is 0. So 2 plus 0 is 2. Oops, 2. Which is indeed our rotation, our rotated matrix. Right? That is now our P1. So that is how rotation matrices work. Right? If you want, you can try this out for, say, for example, like 30 degrees, a 30-degree rotation, something like that. Right? And honestly, that will work. That should work, pala rather. Right? We can try this out again, right? Just to set the example talaga, right? Say, for example, we have here 30 degrees, right? We have here 1 and then square root of 3, and we want to rotate it such that it goes like this. This is now supposed to have a value of 2, right? And that means that if you remember from your trig, this is 30 degrees and this is supposed to be 90 degrees. So in this case, we are just literally adjusting this, rotating this by 60 degrees. So, just like before, your P1 should be equal to your rotation matrix, now in this case for 60 degrees, times your original position. So let's try this out. For 60 degrees, we will have cosine of 60, right? Negative sine of 60, and then we will have sine of 60, and then we will have cosine of 60. You will have here your original position, which is square root of 3 and then 1. And then we will simplify this. Cosine of 60 is 1 half, right? 1 half. And then your sine of 60 is square root of 3 over 2. So this will be negative square root of 3 over 2. This is positive square root of 3 over 2. And this is 1 half. So let's just try and combine all of these things together. We will have, in this case, right, we will have this first, right? We will have, square root of 3 over 2, right? This times this, square root of 3 over 2. And then this times this is negative square root of 3 over 2, which means if you add them together, you will get 0. On the other hand, you will have this, right? This times this. We will have this times this, which is going to be, the square root of 3's are going to cancel out. They're just going to be 3. 3 over 2. And then this thing is 1 half times 1. That's 1 half. So 3 over 2 plus 1 over 2 is 4 over 2, which means that is 2. Which does indeed follow our logic, right? This is just going to be 0 x coordinate, and then it rises all the way up to 2 for your y coordinate. That is the power of the rotation matrix. And notice that the vector size, or rather the magnitude of this thing, the length of this vector remains the same, right? That is the what do you call this? That is the property of this rotation matrix, right? If you want to go dig in deeper, the determinant of this thing is 1, which means that the length does not get changed, right? If the determinant is some other value, say for example 0.5, you know that it will get scaled down to 0.5, its original value, or that's not even length, it's area. But let's not dwell on that kind of thing, right? But yeah, the rotation matrix is such that you retain the length of your vector, because of course when we're trying to rotate a link, we're not trying to make it smaller or larger, we are just literally trying to rotate it, right? And if you want, right, we have here a 2D rotation. Say for example, you have here, let's make this a little bit bigger. Yeah, say for example, you have here your original vector, which is this blue line right here. And say for example, I adjust it. Actually, I should be able to adjust it. Hold on. Yeah, I can drag this around now. There you go. Right, and this value right here, this red dotted line, or this broken line right here, is the x coordinate. As you will see, it will move around, right? It will move around. And then your y coordinate is this thing, right? And what you can do, what I can do in here, is that I can rotate, right? I can rotate our blue vector, right? This t right here, it doesn't want me to put in theta, so I just put in t, right? This is in terms of radians. I can do a rotation if I drag it around, right? And in this case, we will have pi over 2, right? This is pi over 2 roughly. And you will go to pi, which is a full 180-degree turn. And then 3 pi over 2, and then 2 pi, right? So I can just put this and animate it, right? As it goes around and around, right? But our original vector in there is the red line, and you can just adjust, right? There it is. We're adjusting. And there it is. Okay. Yeah, there you go. Okay. Now, you may have seen this. Please do not mind that. We will have that on Wednesday, right? But for now, let's just have these 2D models so far, right? That is what we do when we want pure rotation. The last bit is a combination of these two. If you have this, you can now translate and rotate at the same time. How does that happen? That is what we call a homogeneous transformation, right? A homogeneous transformation basically can perform both a translation and rotation, but you're going to have to perform a little bit of mental gymnastics for you to be able to use a homogeneous transformation. More specifically, it's gonna look like this. And it doesn't seem very scary until you remember the fact that your r theta in here is a matrix. And your displacement here is also a matrix. So this is going to be a little bit bigger than what you originally see in here. More specifically, for a 2D kind of motion, right? I will now go immediately in here. For kind of 2D motion, what you're going to have to do is extend your position vector by 1 dimension. So you're like, what? Right? Say, for example, you want your point, you want your link. Where should I put this? Maybe I should put this here. Okay, there you go. You want your link x and then y. You want your link for it to be from here. Let's have it at an original position of 1 3. 3 1 pala rather. And what we want to do is we want to rotate it and translate it such that it is now in here. Right? So as you can see in here, there is a 90-degree rotation, right? There's a 90-degree rotation, and there is also a movement from here all the way to here, right? So if we're thinking about it, this thing is kind of just like rotated here. This is the intermediate kind of step, right? You rotate like this by 90 degrees, and then you move it around with this displacement vector, which is going to be, if you're going to look at it, right? If you're going to look at it, that displacement vector is going to be, ano ba ito? -2 and then -3. -2 and then -3. What you can definitely do is do something like this, right? For you to get to your P1, what you can do is just P1 is equal to your rotation matrix of 90 degrees times your original position, right? Plus your displacement vector. That's fine. But if you want to do it in one matrix only, you would have to do a homogeneous transformation, right? A homogeneous transformation, literally in the sense of P1 is equal to H times P0, right? What is this H going to have to be? Well, first, we can't ask that yet because this is not the correct size, right? If we remember, our H, right, is just written down like r theta, and then our displacement vector in here, and a bunch of zeros and a 1 in here. So you're saying, wait a second, our theta is a 2 by 2 matrix. And the displacement is a 2 by 1 matrix. So instead, it really is something like this. Cosine theta, negative sine theta, cosine theta. And now this is your delta x and then delta y. So what is the 0 gonna be in here? The 0 in here is actually a 0 vector. Literally just like fill these up with zeros and this with 1. So this is your 2 by 2 homogeneous transformation matrix. And so you're going to notice, wait a second, why is it 3 by 3? Right? Why is it 3 by 3? Why are there 3 rows, 3 columns? I can't use this with my P0. My P0 is 3, 1. That is why you're going to have to add at the bottom, right? At the bottom, you're going to have to add a 1, right? Just trust me that there's a 1 in there, right? So this is your P0, P0. And what you're going to get from this transform is your P1. And we are expecting as well that there's a 1 at the bottom. Okay, so let's see what's going to happen now, right? Now, what we're going to have is something like this. Let's just try again our rotation matrix of 90 degrees, right? Cosine of 90 is just 0, and then 0, and then this is negative 1, and this is positive 1. Okay, so let's have this. This times this, we will have 3 times 0 is 0. Negative 1 times 1 is, let's fill this out then as well. What is our displacement matrix? That is negative 2, negative 3. Negative 2, negative 3. Actually, let's just rewrite this. Okay? Let's rewrite this. We will have a rotation matrix of 0, negative 1, 1, 0. And then we will have negative 2, negative 3. So when we put this together, we will have this times this. This is 0 times 3 is 0. Negative 1 times 1 is negative 1. And then negative 2 times 1 is negative 2. If we add all of that together, we will get negative 3. Negative 3. And then we will go on to the next row. This times this. 3 times 1 is 3. 0 times 1 is 0. Negative 3 times 1 is 0. Negative 3. So 3 minus 3 will give us 0. And then this times this, finally we will have, right, this times this. 0 times 3 is 0, 0 times 1 is 1, and then 1 times 1 is 1. So if you add all of that together, you will get indeed a 1 at the very end. So in this case, what we're just looking at is this negative 3, 0 compared to this 3, 1. So you might be wondering, where's this negative 3, 0? It's this thing. Right? It's that thing now. Right? It's from the origin to where the P1 is supposed to point. Right? So indeed, we have translated and rotated this thing up until a point where we can now just model it with one matrix. And honestly, you can try and do the same thing naman here, right? Let's just try and do it very quickly. 0, negative 1, 1, 0. You will have here an original of 3, 3 and then 1. And then plus your negative 2, negative 3. You will have in here, I'll just do this very quickly, right? This times this will be negative 1. And then this times this will be 3, right? And then you can just add them together. Negative 2, negative 3. You will get your original value of negative 3 and 0. Right? So both of them are going to give you the same thing. It's just that the homogeneous transformation, if you're willing to do a bit of gymnastics here of adding this extra row and this extra entry, if you're willing to do that, then that's completely fine. That is the foundation of our homogeneous transformations. And well, the lesson is supposed to end here. But we know that this is not enough because this is only a 2D representation. We're undeniably going to have to go into 3 dimensions, and I will reserve that for our lesson on Wednesday, right? So you can ask me questions then if ever any of you get super mega confused. Okay? So that will be it for now. yeah, that does round up the discussion, right? 55 minutes. If you guys have any questions, please do let me know, right? I understand that this thing is a sudden shock for everyone. Sudden na nga, shock pa. Yeah, this is a shock for everyone that this is included in machine elements, but after this we will have more concept related things, right? Like in cams, screws, gears, and belts, right? We will have that towards the second part of our MACHELM. But for now, we will have to deal with the math part. Okay? So, again, any questions? Please let me know. And I hope you guys have fun watching this. Thank you.